So whenever you're ready, please go ahead.
Thank you, Moses. Hello, everyone. My name is Viksit Kumar, and as Moses mentioned, I'm an instructor in investigation at Harvard Medical School and Massachusetts General Hospital. Here at Center for Ultrasound Research and Translation, we work on both the acoustics aspect, the machine learning aspect, as well as the translational aspect of ultrasound research. So with this, I'll present a few slides on ultrasound physics. So to go back into the history of ultrasound, first, what is ultrasound? Ultrasound is sound waves of frequency exceeding the range of human hearing, which is at 20 kilohertz. So the history goes back to World War II, when the German U-boats were posing a lot of challenge for the Allied ships transporting soldiers and supplies through towards Europe. So the German U-boats were creating a lot of problem for them. So sonar was developed to sound navigation and ranging. And this was basically long arrays that were towed along with the ship. And they could be both active and passive arrays. So in active arrays, you would basically ping for an object. And once these sound waves strike a U-boat, they would get a reflection back. And you can identify in which direction and how far these U-boats were. Or there could be, now they have passive arrays also where you don't ping anything, so you don't reveal your location, but you just listen for the U-boats and submarines, and they can, from the noises that the U-boats or submarines make, you can hear and you can identify at what range and in which direction those boats are, or those submarines are. So if we go below the hearing, below the 20 kilohertz range, we can even see the use of sound waves in medical sciences. And that is basically the prevalence of stethoscope. So stethoscopes use a very similar concept in which we passively listen to the sounds coming from inside the body. The only difference is that in the frequency range that we are operating in is in the hertz range. So we're somewhere between 50 to 2000 hertz. And that's the difference between a stethoscope and an ultrasound-based imaging modalities. Ultrasound is more image-based. Stethoscope is only listening. So here are some of these early ultrasound research that was done on brain. And here's an echoencephalography image. This is around 50s that was created, and you can barely visualize anything. So things have changed a lot since those times. And now you can see very nice ultrasound-based images from inside the body. So medical diagnostic ultrasound uses ultrasound energy and based on the acoustic properties of the body to produce static or dynamic images. The ultrasound frequencies vary from 2 to 20 megahertz, and this is a range that we are pushing every day, both on the lower end and the higher end. For example, for transcranial ultrasound, we are now somewhere in the 500 kilohertz range, whereas for superficial organs, for example, like eye, we can be as high as 40 megahertz. So these ranges are being redefined every day in research. So how ultrasound is done is that a short pulse of mechanical energy is delivered to the tissue, and a small amount of this energy is reflected back as an echo, which is typically around 5 to 10% of what we transmit. And the transducer both transmits and receives these echoes and generates an image based on that. So for example, here's a transducer which is transmitting acoustic waves inside the soft tissue, inside the body, and then it receives the same echoes back and generates an image which can be seen on a monitor. So sound, let's talk quickly about sound propagation. So sound is a mechanical wave that propagates through a medium by compression and rarefaction of its particles. So in this particular example, you can see a circular wheel which is rotating, which is causing the piston to move towards right and left. in a periodic motion. When this elastic, assuming that these particles are elastic in nature, when it's pushed forward, it creates a compression. And when it's pushed back, it creates a rarefaction. And this is what creates the sound wave. So when we speak also, we create these compressions and rarefactions that are then travel in the medium. So compressions are usually demonstrated by positive and a refraction by the negative in amplitude. And this is basically showing you on the x-axis, you can see the time, and on the y-axis, you can see the pressure. So if the pressure is high, you're seeing a compression, and if the pressure is low, you're seeing the rarefaction. And typically compression is usually higher than rarefaction for ultrasound imaging. And so this is how the sound propagates in a medium. So with sound propagation, there are three important terms that are associated. One is the wavelength of the sound wave that's traveling. So the wavelength is basically defined as the distance between compression or rarefaction. So if I go back here from, can you see my mouse? I hope.
Yes, we can see your mouse.
Okay. Yeah. So if you can see my mouse, this is basically representing one wavelength. So this includes one compression cycle, one half compression cycle, and one half of the rarefactional cycle. That forms a one complete cycle, which is called the wavelength of the sound wave. And the time it takes to travel this one wavelength is called the time period. If we take the inverse of that time period, we can get the frequency of the sound wave. And frequency and wavelength, if we multiply them together, that gives the speed of the sound wave. That basically tells us how fast a sound wave is traveling in a medium. So these are the three basic parameters that defines a sound wave which is traveling in a medium. So the speed of sound is dependent on two main factors, and it varies from medium to medium. One is the bulk modulus, and the other is density. So bulk modulus is a measure of the stiffness of a medium and its resistance to being compressed. For all practical purposes, we can assume that the bulk modulus for soft tissue or human body is doesn't change much. So majority of the changes in speed of sound in ultrasound are supposed to believe to come from density changes rather than bulk modulus. And just to give you a number, the bulk modulus for water is around 2 gigapascal second. So it's very high in magnitude compared to the density. Density for water is around 1,000, and variations from 950, 1,000 kg per meter cube, and variations from 950 to 1,050 are pretty common. So based on assuming that bulk modulus is almost constant, you can imagine that the changing density will change the speed of sound. So, and there are different mediums which show different compressibility. A high compressible medium like air has low speed of sound, and a less compressible medium like bone has a higher speed of sound. So here are different materials with different densities and different speed of sound. As I mentioned, that we assume that the bulk modulus is almost constant, or the changes in bulk modulus are very small. We mainly focus on density. And the three main materials that I like to point out is air. So air has a very low density of 1.2 kg per meter cube. Then water has a density of 1,000 kg per meter cube. And the third is the soft tissue. When we call soft tissue is basically a composition of a lot of different structures that are present in the body. For example, ligament, fat, muscles, they could all be combined together and given an average name of soft tissue. And we say that the average value is around 1,050 kg per meter cube. And the average speed corresponding to that is 1,540 meters per second. For speed of sound. So this is the most typical value that we see for ultrasound density and the speed of sound. I guess other important parameters I would point out is that the density of bone is much higher, and that also leads to a much higher speed of sound. Similarly, the transducer element, which is the PZT element, has a much higher density and also has a very high speed of sound. Here on the right-hand side, you can see how the frequency and the wavelength are dependent on each other. So when the frequency is low, you get a much bigger wavelength of 0.77 millimeter. And the blue line is basically shown for soft tissue, and the red line is for fat. And as you increase your frequency going down on the y-axis, you can see that your wavelength starts shrinking. And typically wavelengths are in the order of a sub-millimeter that you will see in ultrasound range. So other important parameters from sound physics are pressure and intensity. So since sound energy causes particle displacement, there are variations in local pressure amplitude that propagate through the medium. And this pressure is important, and basically it's related to the intensity. By intensity is proportional to pressure squared. So intensity is defined as the amount of power per unit area, and it's proportional to the pressure amplitude. Typically, as I mentioned earlier, that the compressional pressure is higher than the rear fractional pressure. It's very atypical for us to have high rear fractional pressure in ultrasound. And the unit for intensity and pressure are both dB. So and the reason we use the logarithmic ratio is to reduce the dynamic range in which we measure these values. So when ultrasound interacts with matter, there are a few important properties that we notice. And I want to quickly go through some of them. So one is, these are the few: reflection, refraction, scattering, attenuation, and absorption. So these are the basic concepts of acoustic properties related with ultrasound. So I'm going to quickly walk through some of them. So acoustic impedance is defined as the product of density and the speed of sound. And it's measured in rials, so and represented as Z. So air has pretty low acoustic impedance. It's 0.0004 million rials. And a typical acoustic impedance is around the range of 1.48 or 1.5 million rials. That's the typical acoustic impedance that we observe. If you notice that the skull bone has a much higher acoustic impedance. The acoustic impedance plays a very important role because acoustic impedance determines how the images are generated in ultrasound. What we see in ultrasound is basically the difference in acoustic impedance. So when ultrasound wave is propagating through the media, let's say there are two different media 1 and media 2. And when the ultrasound wave goes from media 1 to media 2, if there are difference in acoustic impedance between the two media, there will be some reflection, and the echo will go back to the transducer. And that is what we observe. So if there was a medium in which there was a homogeneous acoustic impedance, we cannot generate an image from that medium. We generate an image only when we see variations in acoustic impedance. And this also relates back to this formula in which we'll talk about the reflection. So an ultrasound or a sound wave is only reflected back when there is a difference in the acoustic impedance. So if you look at the numerator here, it's basically Z2 minus Z1, where Z1 is the acoustic impedance of medium 1, and Z2 is the acoustic impedance of medium 2. So if Z2 was equal to Z1, there will be no reflection. All the acoustic energy will transmit through, and we would get no echoes back to the transducer. So we won't be able to form an image. And that's why what we are measuring is basically a difference in acoustic impedance through the soft tissue. So this formula gives you, the reflection formula gives you an idea of how to measure the acoustic impedance of how that image is formed because of reflection. So if you look at figure A, you can see that the yellow arrow shows you what's incident, The black arrow here shows you what is the reflection, and the pink arrow is what is being transmitted through. So incident, reflection, and transmission. I'll also introduce the concept of refraction here, and this is very similar to refraction of light, where if an incident sound wave is coming at an angle and not perpendicular to the medium, you would see that if the theta I is the incident angle, there will be a theta R, which is similar as theta I, which is the reflection angle, and then there would be a refraction angle. This refraction happens due to the difference in speed of sound in medium 1 and medium 2. So if medium 2 has a higher speed of sound, then we will see that if it has higher speed of sound in medium 2, we will see that the angle of transmission is more than the angle of incidence. If it's lower, then we'll see that the angle of transmission is lower than the angle of incidence. And that is called refraction. So it's very similar to the refraction of light, where we studied that V sine theta 1 divided by sine theta 2 is equal to V1 by V2. So another concept, this is a major concept for ultrasound, is scattering. So scattering occurs by reflection or refraction. So this is what causes us to get those echoes back. So when we send a sound wave in, there are scatterers, which are small object reflectors with size less than lambda, where lambda is the frequency, lambda is the wavelength of the sound wave that's being sent into the medium. These reflectors reflect or scatter the sound wave. And some of those scattered sound waves come back to the transducer. And that is what is being read by the transducer. So how that scattering happens plays a very important role. So it's dependent upon what the reflector or the scatterer size is, what the density is, how the beam is being sent, how the interactions are happening. For example, if the interaction is specular, where it means that you're sending a beam in, it's being acting like a mirror, and it's basically sending all the reflected beam in one single direction. That's called a specular reflection. Whereas if you have a surface where incident beam is coming in and is being spread throughout when it's being reflected, it's called a diffused reflection. So the scattering determines how we view an object inside the body. And it's dependent on a lot of different factors and what the characteristic texture it will create on the grayscale image. Another important concept is absorption and attenuation. So absorption is the process whereby acoustic energy is converted to heat energy. So since this is mechanical waves that are going into the soft tissue, some of these energy gets absorbed into the medium and converted into heat energy. A quick example is when we are speaking, we can, after some distance, we cannot hear the person properly. So it's because the energy is being lost in the medium. So attenuation is defined as the loss of intensity of the ultrasound beam from both absorption and scattering in the medium. So attenuation is a broader term than absorption. It includes absorption and even the intensity lost due to scattering or the energy that is being sent back. So if you look at this figure, it shows you on the x-axis the penetration depth, and it shows you the relative intensity. So it's been normalized for purposes of visualizing. And you can see that when we have a lower frequency, for example, 2 megahertz, which is represented by the blue line, the attenuation is much smaller and we can penetrate deeper. But as we increase the frequency, our relative intensity falls very quickly because the attenuation is frequency dependent and it causes more of the energy to be absorbed by the media. And similarly, if you look at 10 megahertz, you can barely image up to, let's say, 1 centimeter. So attenuation is a frequency dependent parameter, which is typically represented as dB per centimeter megahertz. On the right-hand side, you see a table which is being represented at 1 megahertz. So the frequency is already pre-specified, but you can see the attenuation values for different medium. For example, water has very low attenuation, whereas soft tissue ranges between zero point 0.3 and zero point 0.8 dB per centimeter. And in this case, it's being measured at 1 megahertz. Attenuation plays a very important role in how deep we can image. If you want to image a superficial organ, we cannot use a very low frequency because, sorry, if you want to image a very deep, if you want to image a very deep organ, we cannot use a very high frequency because the attenuation for that high frequency would be very substantial as we go deeper. And that's why we have to use a lower frequency. Frequency is also related to the resolution. So there's a trade-off between resolution, attenuation that we'll discuss later on. So I'm going to talk next about ultrasound transducers. So here on the right, you can see an image of an ultrasound transducers. The role of a transducer is to both transmit and receive echoes for image processing. So, excuse me. So an ultrasound transducer has few main elements. I'm going to walk you through the main elements. One is the piezoelectric element, which you see here in green. This is a piezoelectric element which, when you apply an electrical voltage to it, it generates sound waves which propagate into the media. Then there's a backing element which basically absorbs all the sound waves that go inside the transducer so that you don't have waves traveling inside the transducers and creating noise for you. And then you have an acoustic absorber which does the same. And then you have a matching layer, which makes sure that there's acoustic impedance matching between the piezoelectric element and the medium in which you are transmitting. There's a coaxial cable, which acts as a transmitter and receiver, which basically is to transmit the signals and receive the signals. And then you have a plastic case and a metal shielding. And I'll walk you through some of these components in more detail. So the first component that I want to walk through is the piezoelectric material itself. So it's a quartz crystal or a ceramic. And so they're natural quartz crystals, which can act as a piezoelectric material, or there are synthetic materials like lead synchronate titanate, or which is commonly referred to as PZT. And they have a structure of molecular dipoles. And this is the most common type of synthetic material used for a piezoelectric element in medical ultrasound. So what happens is in a PZT is that if you see in the figure below, this is the equilibrium state for the PZT. So you can see the molecular dipoles. But when you apply a charge to it, or when you receive a compressional wave, the dipoles arrange themselves in a particular fashion such that there's a positive charge on the outside and a positive charge on the front face and a negative charge on the back face. And that's basically how the dipoles arrange themselves in a compression. And similarly, when they are expanding, they become horizontal, where the positive and negative dipoles are arranged such that there's a negative charge on the front face. Excuse me. So this is how basically a PZT can both generate electrical energy into mechanical energy by deformation of the crystal structure, and also receive ultrasound echoes and convert them to electrical energy. The PZT approximately has a low efficiency around 50%, and we lose a lot of electrical voltage when we're receiving these echoes. So they typically operate at very high voltages, which are around somewhere around 50 to 100 volts. In some cases, they go as high as 120 volts when they transmit, but when they receive, they are usually around 5 to 10 volts when you get the signal back. The other important part is the damping block. It's the layer on the back of the piezoelectric element. And what it does is that it absorbs the backward directed ultrasound energy, and it attenuates any stray ultrasound signals from the housing. So when the piezoelectric element vibrates, it vibrates in all directions. There's no particular direction in which it vibrates. So it's vibrating radially, it's vibrating axially, and that creates a lot of unnecessary vibrations. And we only want a directed vibration going actually into the medium. So any other energy needs to be absorbed by this damping block. And that's what the role of this damping block is. So in ultrasound, what we do is we typically create a very short spatial pulse length, which is typically around 1 lambda or 2 lambda. And that is necessary to preserve the actual resolution. And we'll talk about that a little bit. But if we create very long pulse lengths, these damping blocks help us in reducing the transducer vibration. And there are some specific use cases in which we go up to 6 lambda spatial pulse length. So in those cases, the damping block play a very major role in absorbing the extra ultrasound energy that goes inside the housing. Another important thing that I mentioned was the matching layer. So if you recall, the PZT has a very high acoustic impedance. Both the speed of sound and the density for the PZT is very high. So if I recall correctly, it was around 7 million reals acoustic impedance for the PZT. Whereas when you're going into the soft tissue or the medium that you're imaging, it's around 1.5 million reals. So there will be a huge reflection going from the PZT to the human body. So to avoid that acoustic mismatch, the impedance mismatch, we have a matching layer, which reduces the impedance mismatch between the soft tissue that you would be imaging and the PZT impedance. And that's called the matching layer. So there are different types of transducer arrays, and there are two common mode of activations used to produce a beam. One is called a linear array, and the other is called a phased array. And I'll delve a little bit deeper into linear and phased arrays. So a linear array typically consists of 128 to 512 elements. So for example, if you see this figure, you can see a linear transducer. This linear transducer has piezoelectric elements present here. And these piezoelectric elements are diced into 128 or 512, up to 512 elements. That's the most common numbers that we use for medical ultrasound. These elements are diced so that they can be fired as sub-apertures. So this, if you take all these elements together, this is called the aperture of the transducer. But if you take a small subset of elements, this is called the sub-aperture of a transducer. So for linear arrays, we typically use sub-apertures to create images or a subset of transducer elements. Within an element, there are two important parameters that we want to know. One is the width of that element, and the other is the height of that element. So remember that the piezoelectric material is vibrating in all directions. So that's why both width and height play an important role in ultrasound imaging. And we'll talk a little bit more about this later, the role of width and height of a transducer element. But in linear arrays, the simultaneous firing of a small group of around 16 adjacent elements is used to produce an ultrasound beam. So for example, if I want to focus my ultrasound beam, let's say at this point, what I would do is that I would fire these 16 elements in such a targeted fashion that they all focus at this point. And that is done by creating electronic delays in firing of these elements. And I'll talk about that a little later. Uh, and once this transmitted beam travels into the medium, some of that will get reflected back and received by the same transducer. Uh, Once it has switched from transmit mode to receive mode, it will receive these echoes, and then these echoes will be used to generate an image. So from this transducer, you can also talk about the field of view in which this transducer would be looking at. So there are two types of linear array. There are two types of arrays. One is a linear array and other is a curvilinear array. A linear array looks like a straight or a horizontal array, whereas a curved array is a convex array. And we'll see some of images of convex array later. But the field of view for a linear array is rectangular, and the field of view for a curvilinear array is trapezoidal. So phased arrays operate a little bit differently. They usually contain around 64 to 128 element, and rather than firing sub-apertures of these elements, we fire all the elements together. And phase arrays are usually meant for operating in environments where you have limited acoustic window. For example, if you're trying to image an organ which you can only image through the intercostal ribs, there's very little space there, and there's a very small acoustic window to look inside the body. So you need very small transducers which can look inside the body and can also be steered. By steered, I mean that rather than focusing the beam in the field of view, you would focus it outside the field of view. So the beam can be steered. So the steering, since steering requires that the distance between the center of one element to other be less than lambda by 2. The lambda is the wavelength. Phased arrays are constructed in such a way that their distance between the two center elements is usually less than lambda by 2, so that they don't create grating lobes, which can create problems for steering of these beams. So I want to talk a little bit about ultrasound beam properties. So the ultrasound beam propagates as a longitudinal view away from the transducer into the medium. And the ultrasound beam has two distinct beam patterns. One is the near field of the ultrasound beam, and the other is the far field. This is also called the Fresnel zone of ultrasound, and this is called the Fraunhofer zone. In the near field, what's happening is that the ultrasound waves are converging to a point, to a target region, and in the far field, they start diverging. And that's where the difference between the two regions come. At the middle of these two regions is the focus, where the ultrasound beam is being focused. And this is the point where you have the smallest beam profile, and it gives you the best lateral and axial lateral resolution. So as I mentioned, that the element height and width play a very important role. The element width determines where the near field ends and where the far field starts. So the near field is determined by d squared by 4 lambda, where d is the diameter. So the element width times the number of element basically gives you the diameter d. And this determines where the near field will end. Similarly, so in ultrasound, there are, I want to quickly define the axes. So in ultrasound, we define this as the axial or the z-axis. We define this axis as the lateral or the x-axis, and the in and out of plane axis is defined as the elevational or the y-axis. The element width is being measured in the lateral direction, and the element height is being measured in the y or the elevational direction. The beam profile here, it's not a 2D profile, it's a 3D profile. So right now it's being represented as a 2D, but it's actually is a 3D profile. And the element height determines the near field in the elevational direction. So the near field, which is also called the Fresnel zone, has a converging beam profile, and the near field is dependent on the transducer diameter d and the propagational wavelength lambda by this formula d squared divided by 4 lambda. The near field also determines the lateral resolution. And as I mentioned, the lateral resolution is the best at the transition between near field to far field, because the beam profile, it's the smallest at that location. So lateral resolution is mainly dependent upon the beam diameter, and that's how we determine the lateral resolution. So lateral resolution is poor in areas which are either close to and from the transducer because of the spreading of the beam profile. The next concept that I want to introduce is transmit focus, and this is very similar to the near and the far field concept. What we typically do is that we focus these transducer elements at a point, and you can say that this is the region in which the beam has a converging profile, and this is the region in which the beam has a diverging profile, and this is the focal spot of that transducer. Uh, this whole region is called the focal zone, and typically it's around in the range of a few millimeters. We can focus at any given distance, but for particular applications and particular transducers, there will be some natural focus zones, depending upon how the transducer is constructed and what application it's being used for. How the focusing is done is that we know that if we want to focus at this point, the elements which are at the very edge of the transducer will take more time to travel from this end to this focus point compared to the elements which are at the center. So the center elements will travel the fastest and the edge elements will take the most time. So we can individually fire these elements such that they all approach at this particular point at the same time, so that their intensities can sum up in a coherent fashion. So this means that this first element and this last element here are fired first, and then the second and the second last element is fired, and then so on until you come to the center elements. And then you can see that how this delays are being created such that these transmit waveforms uh, come to this point at the same time and interfere constructively to give you an increased intensity. This distance is called the focal distance, and we can focus at any point in the imaging plane. So we can focus at this point, or we can even focus outside the field of view. So I could have focused this transducer here, but the amount of energy that I'll get back from this point is limited compared to what I would get when I focus inside the field of view. But nowadays we have the ability to program these delays, and that allows us to try a lot of different focusing technologies. So in phased array, there is a little bit difference than the linear arrays. In linear arrays, we were focusing a subaperture. In phased array, we focus all the transducer elements together. And I guess I'll go to the, okay. So on the receive side, also we can focus, and I'll show you by looking at this image. So on the receive side, also what is happening is that if there is a scatterer present here, it's reflecting these sound waves back to the transducer. And different scatterers will reflect the sound waves at different times. And so what you are basically getting at one of these channels is a time signal, which varies with time and depth. So if you want to focus at one particular point on the receive side, you can choose where that point is in the field of view, and then based on the distance from the element at which you are looking at that signal, you can decide how much you want to delay your receive signal. For example, if we are getting 100 100 column long signal on the first element, we know that it takes more time for an echo to travel from here to the end element compared to the center element. So we may end up taking like the 50th uh, receive received value from the end element, and we might take the 35th received value at the center element, because we know that the center element travels faster. So on the receive end also we can focus, and that allows us to sum these signals coherently. So that's called receive focusing. Uh, and in dynamic receive focusing, the difference is that we change our delays depending upon how deep we are imaging. So the deeper we go, we know that more time it will take for these echoes to come back to us. So we will delay a receive signal by a bigger amount. And that's what is called dynamic receive focusing. Then there's the concept of dynamic aperture. So those of you who are interested in natural image photography, uh, you would see that there are lenses which are sold with different F numbers. And F number is basically defined as the depth at which you are imaging divided by the aperture size. So the dynamic aperture is also a process of controlling the F number. So ideally, if you want to image at a depth, at a very high depth, your aperture needs to be also very big. However, there are limitations on what the aperture size could be because because of the physical size of the transducer. So dynamic aperture basically tells us at how many elements should we be receiving in the array to create a good image. And it again goes back to a particular application that you're interested in and what F number you want to use. Some other concepts that are important for ultrasound beam perspective is the main beam and the side lobes. So when you transmit an ultrasound, you have a main beam, and then you have these ultrasound beams, which are side lobes. So these side lobes are created because the piezoelectric element vibrates in all the directions. And these are created by the radial expansion and contraction of the transducer element. It creates a side lobe which is not aligned with the main energy that's being sent out. These side lobes can create problem for the main beam, because if there is a very strong reflector or scatterer that is present, it can reflect these side lobes and interfere with the main beam being reflected from a less strong reflector or scatterer. So that can create artifacts in the images. And that's why side lobes are an undesirable beam property that we want to avoid. Another undesirable beam property is the grating lobe. And so here again, this is the main lobe, the side lobes, and grating lobes. Grating lobes are even further off than main lobe. And these are a consequence of the discretization of the transducer elements. We have to discretize the elements because we want to focus them. And to focus them, we want them to have a delay between different elements. And that's why we have to discretize them. However, this discretization and the non-continuous element surface creates the presence of these grating lobes. If the grating lobes can be minimized if the distance between the center of one element to another element is less than lambda by 2. However, that creates a lot of manufacturing challenges, as well as that creates a huge number of elements for the array of same length. So grating lobes are sometimes artifacts that we have to live with depending upon the application. However, they can be avoided and are avoided in phased arrays, where the distance between the center of the two elements is around lambda by 2. And it's important to avoid them in phased arrays, because in phased arrays, you are steering your image to look outside your field of view. And grating lobes, when you steer, if you're going at an angle, grating lobes can create problems in steering. So that's one of the reasons why we avoid grating lobes. I guess the next important metric for ultrasound is the spatial resolution. And this is an important metric which is often compared among different modalities. And ultrasound has 3 different resolutions that we can measure. And the first is the axial resolution, which is basically measured in the Z direction. This is the axial resolution, and the other important metrics is the lateral resolution, which is measured in the X direction. And the last is the slice or the elevational thickness, which is measured in the Y direction. So axial and the lateral resolution are 2 more important matrices. And axial resolution is usually constant throughout the image, whereas lateral resolution varies based on the beam profile. So the lateral resolution is smallest when you are at the focus, and it's higher as you go down in depth or if you're closer to the face of the transducer. So this defines the spatial resolution. There are more, there are technical ways of defining axial and lateral resolution, and it's defined as the full width half maximum of an intensity profile for a point spread function. But I guess those are details that I will not delve into right now. So axial resolution is also known as linear range, longitudinal, or depth resolution. Axial resolution is the ability to discern 2 closely spaced objects in the direction of the beam. And achieving a good spatial resolution requires that the reflectors are at least half spatial pulse length away to avoid the overlap of returning echoes. Spatial pulse length, as I mentioned earlier, varies based on application. Typically, it's between lambda to 2 lambda. So if the reflectors are less than lambda by 2 or lambda, we might have challenges in differentiating those reflectors. And that's the limit of the axial resolution that we have. So in this figure, you can clearly see that here there are 2 reflectors. Reflector 1, reflector 2. When the reflector 1 and 2 are further apart by more than half the spatial pulse length, we receive 2 different echoes that we can resolve. But if they are less than half the spatial pulse length, the echoes will overlap with each other, and we would not be able to resolve them. And that's basically how we define axial resolution. One way of resolving these 2 reflectors is that we can reduce the spatial pulse length. And to reduce the spatial pulse length, either you can reduce the wavelength, which means that you can go at a higher frequency. So if you go at a higher frequency, the same 2 reflectors can be resolved now. Or the other option is that when you transmit, you don't transmit 2 cycles. You reduce it to 1 cycle or half a cycle. However, the amount of energy that you transmit into the medium is also dependent upon the number of cycles. So if you transmit 2 cycles, you are sending a considerable amount of energy into the medium, and the signals that you would get from the reflected echoes would also be proportionate to that. However, if you transmit only half a cycle, the amount of energy that you're insonifying the medium with is very limited. And so that will give you a very poor signal to noise ratio for the signal that he'll get back. So spatial pulse length basically defines the axial resolution. And the axial resolution remains constant with depth. It's not a factor of depth. However, lateral resolution is different. Lateral resolution is basically the ability to discern two closely spaced objects perpendicular to the beam direction or in the x direction. Uh, the beam diameter determines the lateral resolution. So as I mentioned, that closer to the focus, you have the highest lateral resolution, and away from the focus, either closer to the transducer face or away from the transducer, you have poor lateral resolution. So the lateral resolution is a function of beam diameter. So here's an example. So there are 1, 2, 3, 4, 5, 6, 7 points that are being visualized in this image. And the center point where the ultrasound beam is being focused is 4. And this should be the point where the beam profile is the narrowest. And this should give us the best lateral resolution. As the beam profile close to the transducer phase is bigger, we would have poor lateral resolution. And similarly, as we go further off, we'll have poor lateral resolution due to the beam profile diverging. So if you look at the image that's formed from these point targets, you can see that the lateral resolution is the smallest for the center point, and it increases if you go away from the transducer or towards the transducer. There's another resolution, which is the elevational resolution that we are interested in. So there are another type of arrays which are called 1.5D arrays. Up till now, we were studying only arrays which had only one linear array, and there was no subsequent rows in the elevational direction. But there are arrays in which you can have linear arrays tagged in the elevational direction to create multiple such linear arrays. And that's called a 1.5D array. So in a 1.5D array, you can focus these at a particular point, and then you will have an elevational focus, and you can define your elevational resolution. When we only have linear arrays, when we have only one of these, there's still an elevational focus because that's decided by the acoustic lens. So to focus all the energy in a particular plane, we use an acoustic lens. Otherwise, our energy will spread in like a hemisphere. We don't want the acoustic energy to spread as a hemisphere, but we want to limit that energy in a particular plane that we are viewing. And that's what we use an acoustic lens for. So an acoustic lens could also have an elevational focus, which depends again on which application you are using. For example, if you're using breast imaging, in which you are imaging superficial organs in the depth of around 2 to 5 centimeters, you want an elevational focus of around 2 centimeters. However, if you're imaging bladder, which is a very deep organ, it can go as deep as 15 to 20 centimeters. You want an elevation focus of around 10 centimeters. So the elevational focus and resolution again depend upon the beam profile and what specific application that you're using. The next topic that I want to touch is how the image data is acquired and how we finally make images. So what we are basically getting is time signals from these different channels, and it requires a number of hardware components to get these time signals into an image. And that's what I want to talk about next. So here is a transducer that is looking into a patient, and it's basically sending out it's transmitting energy or sound waves into the medium, which is then being reflected back and then received by the same transducer. So a transducer has a transmit and receive switch. So when it's in transmit mode, it only sends acoustic energy out. And when it switches to a receive mode, it stops sending energy out, but it starts receiving echoes back. And those echoes that are received back create electrical voltage in the PZT, and that electrical voltage is then recorded. When the transducer is in a transmit mode, it's basically pulsed by different pulsars, which are around 100, which typically are in the range of 50 to 120 volts. These are high voltage pulsars that can transmit energy into the ultrasound transducer. And when we are in the receive mode, there are preamps which are used to amplify the receive signal. If you recall, I mentioned that the receive signal is very small. It's usually 5% of the transmit energy that is being sent in. So there is a need to amplify that signal. And that amplification must be a low noise amplification, because if you amplify the noise also, that creates a lot of problems. So these are low noise preamplifiers, and we want them to be as close as to the transducer itself to reduce the noise. And once we have these preamps, we can digitize the signal using an analog to ADC, analog to digital converter. These analog to digital converter then sends it to a beamformer where the image is delayed. And as we talked about dynamic focusing, it's focused to beam some these images to form, beam some these signals to form the images. And then we go to a receiver and a scan converter, and I'll talk more about these, and then we form an image. And this is how an ultrasound image would look like then. So I'll delve a little bit deeper into these different components. But beamformer is responsible for generating the electronic delays for individual transducer element in an array to achieve transmit and receive focusing and beam steering. So that's the role of a beamformer. The role of a pulsar, as I mentioned, is to excite these piezoelectric elements at a very high voltages so that they can insonify the medium. The role of a transmit receive switch, as I mentioned earlier, is that they switch the transducer from transmit mode to receive mode. So you initially transmit, and once you have transmitted, you switch to receive mode so that you can receive the echoes. And as I mentioned, we operate in the pulse echo operation, and with majority of the time being spent in listening for echoes. So I want to talk a little bit about how an A line is formed. So recall that we use, depending upon the type of transducer, we use either the whole aperture or a sub aperture to transmit energy into the into the medium. And when we transmit energy, we transmit them in a series of sequences. So for example, we would focus at one, let me see if I can find an example here. Sorry. What we do is that we create different A lines which span the whole field of view. And so there are multiple A lines that together construct a complete field of view. So you can imagine that going from left to right of this page, you would have around 128 vertical lines. And those A lines, or the amplitude modulated line, together make an imaging data. So when we send a wave inside, the rule of thumb is that for each centimeter of travel, it takes around 13 microseconds for the echoes to come back. So if we are traveling, for example, 6 centimeter deep, once we transmit, we wait for 90 microseconds for all the signals to come back so that we can store them, and then we move to the next line. And that basically determines what the pulse repetition period for these A lines is. So we usually create a pulse repetition period which is more than the depth that you are imaging. And so for example, if you're imaging 6 centimeter, you need at least 100 microseconds. So you would keep a pulse repetition frequency of, let's say, 150 or 200. You will pad it a little bit. And then the next pulse goes out after 200 milliseconds. And then you create another A line. So if you have 128 transducer elements, you would create such 128 such A lines. And then these 128 lines will be combined together to form an image. So as I mentioned, that the pulse repetition frequency is the number of times that the transducer is pulsed per second, since we have to pulse every time we form an A line. So that's the reason for pulse repetition frequency. And it typically varies from 2000 to 4000. And it's basically dependent on the imaging depth that you are looking at. If the imaging depth is very high, you have to wait for a longer period to listen for the echoes, and that determines how long your PRF would be or how short your PRF would be. So I would also mention that high ultrasound frequency has limited penetration depth, because as you increase the frequency, the attenuation also increases. So the amount of energy absorbed by the medium is much higher, and thus allowing only to look at limited depths, but that allows us for a higher PRF. And higher PRF also translates to higher frame rate. So the next thing that I want to talk about is the preamplification and analog to digital conversion. So in this multi-element array transducer, everything is being performed in parallel. So these returning echoes are being recorded in these time signals. And then there is a summing circuit which sums all of them. All of them are based on these digital dynamic focusing that we do. And that's how we get the digital output. So the role of the ADC is to convert this analog signal into a digital signal. And once we have digitized the signal, then we can apply any delay that we want. So depending upon where we are focusing these returning echoes from, we can decide on the different delays that we want to apply to focus at a particular location. So for example, if you are focusing here at this point, you want this element to have the smallest delay and this element to have the longest delay. Or if you're focusing here, you want this element to have the smallest delay and you want this element to have the longest delay. So depending upon where you are focusing in the field of view, we can change these delays and then sum up these time signals, delayed time signals, to get a digital output which creates a single A line. On the receiving side, the signal that we receive, it goes through a lot of different operations. So the receiver accepts data from the beamformer, which represents the echo information as a function of time. So for example, if you see on the right, here is an amplitude signal that's being detected. Once it's being detected, it's pre-amplified. Again, as I mentioned, these are low noise amplifiers. So they try to reduce the noise, but increase the amplitude strength. And this is because the piezoelectric has limited efficiency in converting the signal back. So that's why a preamplifier is needed. And then there are further operations that we perform on this signal. These operations can be tuned by the user or the receiver itself. And these are the operations that we perform. One is the time gain compensation. The other is logarithmic compression, demodulation and envelope detection, noise rejection level, and process signal. And I'll go through all of these one by one. The first one that I want to talk about is the gain adjustment. So if you look at the signal as a function of depth, so on the x-axis we have depth, and on the y-axis we have amplitude, you'll see that the amplitude decreases as we go down in depth. And that's because of the attenuation, which is an exponential function. You can see an exponential decrease in amplitude. So what we do is that we amplify a signal in an exponential by multiplying it with an exponential, and that increases the amplitude of the signal. So if this is the original signal, we multiply it by a gain, which is exponentially increasing with depth, we can get a signal which is after TGC looks very consistent. And now if we were to do demodulation and some more rejection, we can even make the signal look better. So if we take the envelope of this signal, we can see this is the envelope of the signal, and that's what we see here. And this is how an A line would look. And we would reject any of this negative signal and just look at the positive signal. And this is how an A line would look. So this concept of increasing the gain as a function of depth exponentially is called time gain compensation. And we use the word time because time refers to the depth, because as we go deeper, the more time it takes for the echo to come back to us. The other concepts that I want to quickly touch base on are rectification, demodulation, and envelope detection. So rectification is the process of inverting the negative amplitude signal of the echo to positive values. The demodulation is a concept which comes from frequency modulation, which is used in radar. In radar, what we do is that we typically send the transmit signal on a carrier frequency, and that carrier frequency, which is called the frequency modulation technique, is basically rather than doing amplitude modulation with a signal in which the amplitude changes reflect the changes happening in the medium, we rather convert it into frequency modulation, which means that changes in frequency reflect what happens inside the medium. So the signal is basically carried on a center frequency or a carrier frequency, and it basically what's happening inside the medium is that the frequency is changing as the signal comes back to us, and we can demodulate that signal and remove the effect of carrier frequency and then look at the signal at a baseband level. The envelope detection is similar to what I showed here, in which you have an amplitude and you can take the envelope of this amplitude. So as you look here, this is the envelope of this amplitude, and that's called the envelope detection. Rejection is a process in which we reject signals which are very small and probably are noise coming from the ADC or any other electronic noise that's being generated. And so there are adjustments in which you can reject some very low amplitude signals. And processed image are optimized for grayscale range and viewing on the limited dynamic range monitors that we have. So there are 3 different echo display modes. And I think I'm coming to the end of the talk, so I'm going to rush through some of these now. So echo display modes are the 3 different modes. One is the amplitude mode, the other is a brightness mode, and the third is the M mode. And here is a, So amplitude mode is basically looking at the amplitude of the signal that is being reflected back. It's a single amplitude line that we look at. If we take multiple A lines, we can create an intensity or a B mode image. And that's what's called a brightness mode image. An A mode in which the x-axis is time is called an M mode. So if you're looking at a single A mode over multiple, single A line over multiple time periods, that creates an M mode. So that's the difference between A mode, B mode, and M mode. So I want to quickly touch base on electronic scanning and real-time display. So currently we have 2 types of transducer available, linear or curvilinear arrays and phased array. They are distinguished by the way in which the beam is produced and what's the field of view that we cover. So here is an example of all 3. So here is a linear array. Here is a convex or a curvilinear array. A curvilinear array has a trapezoidal field of view, and a linear array has a rectangular field of view. As we mentioned here earlier, that if you use a subaperture of elements, it's called a linear array. If you use the whole aperture, it's called a phased array. And these blue lines show you one A line of a data. And if you combine multiple A lines, it creates a B mode image. So that's the basic concept of linear, curvilinear, and phased array. And a phased array, as I mentioned earlier, are used for steering. And you can see how it's steered. And yeah, again, for steering, we can now use transmit and receive delays, which we have learned about earlier. And we can steer even outside the field of view. So the field of view for a phased array is not just limited to this rectangular region, but it fans out. But this fanning out is not due to the shape of the transducer, but because of the electronic steering of the signal. So another important concept for ultrasound physics is the frame rate. And the frame rate is dependent on a lot of different factors. So the frame rate is basically how quickly that image is refreshed. So for example, if you're imaging liver, how many liver images would you see in 1 second? So for example, you're seeing 20 images of liver in 1 second. That means your frame rate is 20 hertz. So the faster you look at a particular organ, the more dynamic functions of that organ you can observe. And the frame rate is dependent on these main factors. One is the number of A lines that are used to create an image. What is the field of view? What is the line density? And what is the penetration depth? So as I mentioned earlier, that penetration depth basically determines how much time you have to wait for listening for echoes. So rule of thumb, if you're looking for a 1 centimeter penetration depth, you have to wait for 13 microseconds. So the deeper you image, the more you have to wait, and it basically reduces your frame rate. You can increase your frame rate by either reducing the depth or reducing the line density. And when I say line density, what I mean is basically the number of lines that I'm using here. So I can reduce this to a smaller number of lines, maybe only use half of them. For example, here I used only half of them. And then I can reduce my line density, and that will help me or the number of lines and line density, that will help me increase my frame rate by sacrificing the line density. So there are different trade-offs that you can use depending on a particular application that you want. So one way of comparing different modalities is that what are the different matrices that we use. And for ultrasound, there are 3 or 4 main parameters that are used for determining the image quality. And those are spatial resolution, contrast resolution, image uniformity, and noise characteristics. And these quality parameters are dependent upon the transducer frequency that we use, the pulse repetition frequency, the amount of energy that's being transmitted into the medium, what TGC or time gain compensation curve is used, what is the skill of the operator. So it's very much dependent on how all these parameters are set, that an image quality of ultrasound is determined. So compared to other modalities, ultrasound is very dependent upon user skill, as all these parameters can be tuned for a particular application. So as I mentioned earlier, that spatial resolution, both lateral axial resolution, the smaller the lateral resolution, the smaller the axial resolution in millimeter, the better it is. And similarly, it goes for the elevational resolution. So that is one parameter on which we judge the ultrasound image quality. The other more important parameter is contrast resolution. So contrast resolution basically determines what's the acoustic impedance difference between different tissue boundaries and how clearly we can identify one tissue organ from another tissue organ. And again, it's driven by the acoustic properties of the medium. So there are limitations to what contrast resolution we can achieve with ultrasound because it's dependent upon the medium that you are imaging. But one quick technique that improves the contrast resolution is how much compression is applied by the ultrasound transducer. So when a sonographer takes a transducer and images a particular organ, they can compress the soft tissue, and that usually increases the contrast resolution. The other factors that are important are density and the size of scatterers within tissue and organ. And again, it's the medium property which defines what the contrast would be. Then ultrasound scattering, how these reflectors are scattering the images, if they are coherently adding up or they are being destructive. That also determines the contrast resolution, and spatial resolution also plays a role in how the contrast appears. So contrast resolution can be improved by use of microbubble contrast agents. These are small gas bubbles that are introduced into the vasculature, and which have very high acoustic impedance, and so they create a huge reflection of the echoes, and that's why how you can clearly identify where the microbubble is, and that improves the visualization of the vasculature and how the tissue perfusion happens. Another way of improving contrast resolution is spatial compounding. That means that you average multiple B modes to get a better understanding of the speckle pattern, and reducing the stochastic speckle noise or the electronic noise that is present. Another method is that we can look at harmonic images. So what harmonic images do is that they eliminate the fundamental frequency, which is more susceptible to noise, and look only at the higher frequencies that are coming back from the echoes. And that's how we create harmonic images. Another technique is Doppler imaging techniques. How they work basically is that they compound a lot of different ensembles. That is, they repeat the same measurement multiple times to improve the contrast resolution. One of the challenges that ultrasound faces is noise, and there is a lot of electronic noise that is present, and we have to make effort to lower that noise. If you recall, I mentioned that we use amplifiers which are low noise amplifiers, and that is one of the effort to reduce the noise present inside the medium. There's some noise created by firing of these elements. Sometimes we use multiplexers, which create a lot of noise. We have these transmit and receive switches, which switch and create noise, electronic noise. And so there are a lot of noises that need to be suppressed for a good image quality. Also, as the signal goes down deeper into the medium, uh, the signal amplitude strength decreases and the noise starts to overpower the signal. And that's why we use time gain compensation. However, time gain compensation multiplies both with amplitude and noise, so it increases both amplitude and noise. So that's the challenge of using time gain compensation. Noise can be reduced by temporal or spatial averaging. So it's a similar idea that I mentioned before for improving contrast resolution. It could be used in low power operations. So for example, in some obstetrics applications where we use very low transmit signals because of FDA guidelines on what intensity of a sound wave should be sent in for different biological tissues. For fetal tissue, we can use very low power operation. So that requires even higher signal amplification. and that makes the signal more susceptible to higher noise levels, and it reduces the low contrast to noise ratio. Where possible, we would like to increase the transmit power and or the pulse repetition frequency so that we can improve the contrast resolution. However, the amount of energy that we can send into the biological tissue is governed by the FDA. And typically, in terms of intensity for peripheral organs, we are limited to 720 milliwatts per centimeter square of energy that we can send into the body. Uh, there are a lot of artifacts related to ultrasound imaging. Uh, I think in the interest of time, I might skip this portion. Moses, do we have time for questions, or should I continue?
Yeah, so if people need, if everyone is, or if anyone has to run, please feel free. And if you have questions, you can email me or Vixit with the questions later. But as long as everyone doesn't mind, I think we can stick around for a few extra minutes for questions.
Okay. So if it's okay, then I'll go through the rest of the slides quickly. So there are multiple artifacts that are associated with ultrasound imaging, and I'll go through some of these artifacts quickly. So refraction artifact is present when we have two medias of different speed of sound. And what happens is that due to the difference in speed of sound, a tissue organ might look discontinuous. So for example, it's going straight here, and then you would see either a bending of the tissue line or a discontinuity in the tissue line. And that's called a refraction artifact. Another common artifact is shadowing and enhancement. So for example, if you look at this particular organ, this organ is very highly attenuative. So it absorbs almost all of the ultrasound signal that's being coming from the top. And basically you cannot see anything below it. And that is called acoustic shadowing. This organ is an opposite of the organ on the center, and this has a very low attenuation. So since it has a very low attenuation compared to its neighboring signal, uh, this signal amplitude is higher, and this creates an acoustic enhancement. So if you look at the image here, this is a very low attenuating tissue, and it creates an acoustic enhancement here, whereas this is a highly attenuative tissue, and it creates an acoustic shadowing. Sometimes what happens is that close to an organ, there is a reflection from the organ, which creates shadowing. And here is an example of the shadowing. So this is being created by reflection from this surface, and this is creating that shadowing. So this is some of the artifacts that are associated with ultrasound images. Another common artifact is reverberation. So what happens is that whenever there is two closely spaced interfaces, ultrasound wave can get stuck in those interfaces. For example, there is an air interface here, and what happens is that the ultrasound signal comes here. Since the impedance mismatch between the soft tissue and air is high, it gets reflected back, and it is received by the transducer. But some of that energy is again, after some time, again gets reflected back, and that creates a reverberation. So you will notice that sometimes what we see is that we see multiple reverberation of the same air surface. For example, here is a layered structure which has reverberations present here because of multiple reflections happening within this layered structure and multiple echoes going back at different times, creating these reverberations. One common problem is that we have to estimate the speed of sound when we are beamforming, because to estimate the delays, we know the distance between a point and the element that we are interested in, but we also need to know the speed of sound to calculate how much time delay we want to apply to a particular element. And that's where the speed of sound plays an important role. However, the speed of sound varies by organ to organ. So for example, fat may have a lower speed of sound than the liver. So what happens is that when you look through fat, if there's a fat globule here, it would create the sound wave will travel slower here, and basically there would be a discontinuity in the liver boundary, in the liver capsule, and this discontinuity is because of the presence of the fat globule here. So here, if you look at this image, this is the liver boundary, and suddenly you have a discontinuity here. So this is because of the speed that's being used to reconstruct these images. We typically use a constant speed. However, good beamformers can account for local speed of sound and correct for these sudden shifts in the speed of sound. As I mentioned earlier, there are side lobes and grating lobes. They can also create problems. So here is an example of a gallbladder being imaged, and you can see this pseudo sludge because of the presence of side lobes. And if you look at the same image in an alternate view, you do not see that sludge. And that's because the side lobes are creating these artifacts. Grating lobes, again, as I mentioned, creates problem. I don't have an image to show for grating lobes, but I guess I discussed a lot about grating lobes, so I'm going to skip that. Another common problem is mirroring of images. For example, in diaphragm, this is what we commonly see in liver and diaphragm, that the diaphragm gets reflected back here. The liver tissue appears below the diaphragm also. So for example, if you look here, you can see the liver tissue here as well as here. And that's because of the reflective nature of the diaphragm. So diaphragm is very reflective due to the impedance mismatch, and it creates a mirror image of the liver tissue. So this is another common artifact that we see in ultrasound. So here are some of the readings that are suggested to help you understand better diagnostic ultrasound and its uses in medical ultrasound. And thank you. And if you have any questions, I'm happy to answer them.
Thank you very much.